So let's take a look at snapshot and history graphs. A snapshot graph is, well, it's named as an analogy to if you were to take a photo of a wave propagating through like a rope, for example, or a wire. So what it's doing is capturing a moment in time. So we've got keeping time constant, right? T is equal to, let's say, 0 is kind of a nice easy one. Okay, so it's a moment in time, and we're looking at, well, what's the displacement all across the rope? So at x in meters. So if we imagine, well, let's maybe, to make things kind of very nice, let's just add that, the rope is blue, for example. So this could be a physical picture of the rope. I'm not sure how thick I originally made the line, but you get the idea. So the rope is blue, and so what we're seeing is the displacement along the rope. Okay, so we can note a couple of things about this. The entire wave pattern is, well, how wide is it? 1, 2, 3, 4. So it's, the whole thing is a 4 meter long wave. That's going to be important later. Okay, so when we think about waves, there's this relationship between the overall pattern, which is what you're seeing in the snapshot graph, and the perspective of an individual particle or place along that medium. So what do we mean? Well, what's going on at this particular point? What's the experience at x is equal to 6? Let's say that you are at x is equal to 6. I'll draw you in a little fine detail here. So here's you at x is equal to 6. How do you experience the wave? And that's what we're going to look at with a history graph, is the experience of an individual location along the medium that the wave passes through. Well, the first thing that happens to you is going to be, well, nothing, because there's a bit of distance between you and the wave front. But then the first thing that's going to happen is you are going to climb up this gentle slope up to the peak, and then the next thing that's going to happen is you're going to have that more sharp decline, and then you'll be back to nothing as the wave passes through. Well, let's work that out kind of step by step. Okay, so before we go and try to write the history graph, let's try something which is to draw out multiple snapshot graphs. So why don't we ask ourselves, what does things look like 1 second later? So in blue, we've got t is equal to 0. Well, what about t is equal to 1 second? Okay, well, what we're really saying is, well, where is that wave 1 second later? The only math we really need to do in snapshot to history graphs is to apply v is equal to d over t. That's it. So in this case, in 1 second, how far does the wave get? So what distance does it cover at 1 meter per second? In 1 second, it covers 1 meter. Okay, so the whole thing is going to move by 1 meter. So that means that this point here is going to instead be here. And this point there is in fact going to be here. And this point there is going to be here. Okay, and we can draw this out. And so that's our snapshot graph for t is equal to 1 second. Let's draw a couple more, and we get a sense of how this is evolving over time. Okay, so let's do now t is equal to 2 seconds. Well, it's going to be 1 meter further along. Ooh, this might need to move. Keep it out of the way. We'll just kind of keep it down here as a kind of map for the color. Let's choose purple next. Let's do t is equal to 3 seconds. Just got a few of these so that we get a sense of how this is going to map when we start to think about, because what we're doing here is these consecutive, it's like taking multiple photos of the wave as it passes through. So every second we're going to take a photo, and this is what we're going to see. And in that 1 second, it's going to move 1 meter farther down the rope. Okay, so here we go. I think that's enough. So that's subsequent snapshot graphs, and now we're seeing this illustration of the wave moving along the rope. And as you can see, how much distance it covers along the rope depends on the velocity. Okay. So let's get back to thinking about, well, how does this all connect to what's happening at x is equal to 6? Well, remember, what's happening is first we start at displacement is 0. So let's start to actually draw this out. So in blue, we're going to have x is equal to 0. And at that point, we've got a displacement of 0. So let's go down to our history graph and plot that. Okay, what's up next? T is equal to 1. Well, what's happening at t is equal to, oh, it's still 0. Okay, so here we go. Displacement is 0. Now, what's happening at t is equal to 2 seconds? 2 seconds. Well, it's got some displacement, probably a little less than 1. So we can fix this later, but approximately there. And then what's going to happen next? Well, t is equal to 3. We're going to be a little further up, so past 1. We'll draw that there, and then at t is equal to 4, we're going to be, in fact, at the peak. So that'll be 2. And here we go. And so that's the first part of our history graph. And then what happens 1 second later? Well, 1 second later, we're going to be back down to a displacement of 0. So that's the full wave. So let's draw that out, and then we'll unpack it a little bit more. Yeah, so what just happened there? We've got our history graph. Now let's make a few observations. One, it looks like a mirror image of the snapshot graph. And the reason is that when you're taking the perspective of this particular point, the first thing that's happening at t is equal to 0 is nothing. And then what's going to happen is you're going to climb up, right? First you're going to be here, which is here, so you're going upwards. And then you're going to be there, which is up here. And then you're going to be up here, which is up there. So that's the first thing that happens, and you see that nice gentle slope happening first. And then the next thing that's going to happen is you're going back down the steeper slope. Now, of course, you don't have to do all of this work every time to do it second by second. What you really need to look at is the overall pattern. So we know that the whole wave pattern is 4 meters. So this delta x here is 4 meters for the whole wave. And really what we're going to focus our attention on are a few key points. You know, the start, the peak, and the end. And if we know those, then we can fill in all the rest. So if we ask ourselves, well, what amount of time is it going to take before the wave reaches the point of interest? Well, to go a delta x of 1 meter at a velocity of 1 meter per second, well, that's a delta t of 1 second. So that's how we get our start of the wave. And then we can say, well, what about the peak? Right? Instead of doing all that work, we could have said, well, delta x between this position and our peak, that's going to be 1, 2, 3, 4 meters. The peak is 4 meters away, and the velocity is 1 meter per second, and so that gives us a delta t of 4 seconds. Hence, we're at 4 seconds here for our peak. So right away, we could have just drawn that line. And then we can say, well, what about our end of the wave? How far away is that? Well, it's 4 meters plus 1 meter for that distance from the edge of the wave to our position. So it's 5 meters. And so in that case, right, we're going to be 5 meters of distance at 1 meter per second. And that's going to give us a time of 5 seconds. And there we go. So by mapping out the start, the end, and whatever features are important for the pattern, we can draw out the history graph pretty quickly. So all we're doing is applying v is equal to distance over time. So that's our simple example. Let's make it more difficult. Why don't we pick a location for a history graph that is a little less obvious? Let's put it way out, far away, far, far away. So here's the same question, same wave, same velocity, but in this case, we're going to have a distance of 150 meters. Does that make things difficult? Nah, it just means that we have to think about how we do this mapping again. And it really means we're not going to be drawing out all those snapshot graphs again. We're really going to think about, well, how long until this position, the start of the wave, reaches 150 meters. Okay, well, let's give that a try. How far away are we? Well, it's 150 meters is our position of interest, and that is at 5 meters. So the distance between the position that we're interested in and the wave is 145 meters. We also know that the velocity of the wave is 1 meters per second. So that means that the time is going to be 145 seconds for the wave to reach that position. And so let's draw our axis here. So this is 145 and onwards. Okay, I better zoom in to draw my 5s legibly. Okay, so here's a sensible axis label. So what's actually happening at 145? Well, the wave is just arriving, so nothing, didn't mean to do that. So nothing's happening yet. Okay, well, let's think about when does the peak arrive? Well, again, focusing in on the fact that we've got to look at what's the distance between that and we could say the front of the wave is 1, 2, 3 meters. And so if we're starting at 145 seconds, how long does it take the wave to get to the peak? So we could think about it either, we could do it the same way as before, and we could say, well, 150 meters minus 2 instead. Or we could just start at 145 and say how much longer until it travels another 3 meters. And what we know is, well, to travel the time it'll take to travel that extra distance, again, all we're going to be doing is applying velocity is equal to distance over time. And so our time is is going to be equal to the distance over the velocity. So to travel an additional 3 meters at 1 meters per second just takes 3 seconds. So 1, 2, 3 at 148, we're going to be up at this peak point. And then we know that the wave is going to need only 1 additional meter to then go back down to 0. And so that'll take 1 second. And there we go. Here's our history graph for x is equal to 150. I'll do it in red just to be consistent. And notice that it looks essentially identical to what we did for x is equal to 6. Let's just compare. Yeah, that looks identical. The only difference is the time axes. And that should make sense because the traveling wave is going to affect every point the same way. If we look at what's happening here, well, this wave is going to pass through. If we look at this point, the wave is going to pass through. It's going to be the same for every point that is in front of that wave. Okay. Is that the most difficult thing we can do here? No, we can make this one level more complicated, I think. That mapping from snapshot to history was always using a rather trivial velocity of 1 meter per second. What happens if that's not going to be the velocity? Let's make sure we're prepared for that eventuality. Let's try 2 meters per second. What's going to happen there? Well, in that case, we're going to have to do the exact same thing, but be a little bit more mindful of our velocity. We can't just say, oh, it's always the mirror image and just draw it out really quickly. That's not always true. So where's the velocity going to be? Well, let's do the exact same position as we did earlier. Let's say what's going on at position x is equal to 6. And you're going to be at this position, observing what happens and how quickly it happens. That's the key difference here. Okay. So, like before, the first thing that's going to happen is you're going to travel upwards along that gentle slope and then downward sharply. Let's look at these key positions and do the mapping. Okay. So, when does the wave arrive? Right? Well, how far away is it? I'm just going to move this away. We're going to highlight the velocity. It's really important here. Okay, so first of all, easiest thing to do, t is equal to 0. What's the displacement? It's 0. Here's our distance away. Delta x is equal to 1 meter away. So if it's 1 meter away, traveling at 2 meters per second, how long does it take to get there? 1/2 seconds. So that means at half a second, the wave will arrive. So that's the front of the wave. Now let's look at the peak. The peak is going to be, how far away? 1, 2, 3, 4. So that peak is 4 meters away. So if x is equal to 4, v is equal to 2, how long does it take to arrive? 2 seconds. So at 2 seconds, we reach the peak displacement. And now, finally, what about the end of the wave? When does the end of the wave arrive? Well, in this case, the delta x is 5 meters away, traveling at 2 meters per second, and that's 2.5 seconds. And so let's then draw this shape out, and we'll go a little thicker. Oops. Okay, so this is the same exact pattern, right, as before, except that because it's all happening twice as fast, because we've got that higher velocity, it's going to look compressed. And we can think about this as the overall shape, the entire shape of the wave. So the wave is, well, it's how big? 1, 2, 3, 4. So the wave is 4 meters long. And so at v is equal to 2 meters per second, it takes 2 seconds to pass through. Right, so our delta t of the whole wave is 2 seconds. And that's our snapshot to history graph conversion when we have a velocity that's not just one. We can have any velocity, we can use any position and do that mapping. So I hope that this helps. Just to review, got the same exact pattern, just compressed because that velocity is happening, so the whole wave is passing through more quickly. And now what would happen if the velocity was smaller than 1? Well, the whole thing would be stretched out. It would happen slowly. So I hope this helps. If you still have questions, then you can post them and I'll try to help. Thank you.